So there is, I think there's a balance that I have to, that it's always a little difficult because there is diversity in students, and I have students probably here that will find learning R to be useful based on, I don't know what path they go down in the future, where they might be faced and have to use R in the future. And I think that's very likely for some of you. And others of you, you will not have to deal with R ever again. And so there's kind of a balance. How much do we spend in R? How much do we not spend in R? You know, a lot of our course is learning these statistical tests and statistical methods to be done by hand, which is useful in our understanding, but in reality, or from a practical perspective, statistics is rarely done purely by hand. It's almost always involves using a computer program to assist in the data analysis. What we learn from the textbook and learning how to do things by hand, we get a sense of when to use these tests, what kind of results our tests produce, and how to interpret the results of those tests. But the actual tests themselves generally are computed with the assistance of a computer. And there's many different statistical programs out there. And depending on kind of which field you enter, you know, people may use R. They might use SPSS or Stata or SAS, all sorts of different things. Every tool set is a little different and serves a different purpose. Okay, so R, I think, is great because it's free and very flexible. All of those other packages are quite pricey, and so probably not. It would probably not be wise for me to have you, spend several $100s on a package or program that you might only use for a few weeks. So, so that's one of the reasons why I've selected R for the course. R is actually used quite a bit in a lot of data analysis, especially in the academic world and the tech world, but maybe less used in industrial settings, where maybe I would say Stata and SAS still have the upper hand. SPSS has a popular following among social science, because it was specifically designed for that group. Anyway, I'm never quite sure exactly how much R labs I should assign, just because I know every student is different. Every student is taking this course maybe for a slightly different purpose. Some of you are just trying to fulfill some kind of course requirement to apply to a grad program. Others of you are hoping to gain some statistical knowledge and understanding for your career. And so, so just bear with me as we, if you have to deal with R and do some labs that maybe you don't enjoy. But I don't know. Are they really that awful? It's not that awful. Okay. For some of you, it might be awful. All right. So today we are moving on in chapter 5 and 6. And we are going to learn about sampling distributions. And our first exposure to statistical inference. All right, so a sampling distribution is the probability distribution up a sample statistic. So 2 weeks ago, we learned about the rules of probability, and we learned about probability distributions for random variables. Okay? And we said a random variable was the outcome to a random experiment where the outcome is numeric. 2 weeks ago, we learned random variables, the discrete case of random variables. And we said, y could take on the value this with probability 0.5. That was the example with, what kind of winnings you would get from playing Monopoly at McDonald's. We said y could take on the value of 0 with probability 0.7, and it can take on the value of winning something worth $1 with probability 0.3 or something like that. And we learned how to calculate the mean and standard deviation of a random variable. We also applied that further, and we looked at a special case with the binomial distribution, which is also random variable. And we learned that the probability distribution for a binomial variable or binomial distribution, takes on certain values, and there's a specific formula for calculating those probabilities. Last week we looked at the normal distribution, another random variable. Okay, and the probability distribution of a normal variable was continuous, and it has that unimodal and symmetric shape. And we didn't learn any kind of formula or the equation behind this thing, but we said we have a table that gives us probabilities from this normal probability distribution. Okay. So today we're looking at sample statistics. Okay, so what are some sample statistics that we've learned? Like from a sample, what are some statistics you can calculate about this random sample? You can calculate the mean, right? So that's probably the one we're going to focus on the most, is we're going to take a random sample, and of that sample we can calculate the mean of the sample. That's if it's a numeric variable. On the other hand, if we're looking at a categorical variable, what kind of statistics can we calculate from a categorical variable?
Frequency.
Okay, a frequency or a relative frequency, which would be a proportion. Okay, so if I take a random sample, categorical variable, I could say, the proportion that's female or something like that. And I would get some kind of statistic on this sample. Or if I had a numeric variable, I can ask for a statistic on the sample, and it would be the mean of the sample. Okay. What a sampling distribution is that just imagine all the different possible samples that can be taken. Each of those samples would have a different mean. What is the distribution of all those different means? That's what a sampling distribution is. Okay. So imagine what is the distribution? That's our sampling distribution. So for illustrative purposes, we can talk about how we could generate a sampling distribution, maybe the quote-unquote hard way. So we might have a population. Population has lots and lots of people in it, or lots and lots of items. The population is huge. But maybe we aren't looking exactly at the population itself. Maybe from the population, we draw a sample. Let's say 12 items. N is equal to 12. And I'm going to calculate the mean of this sample. And I'm going to record that. Okay. Then maybe I take another sample. Another sample of 12. And I calculate the mean of the second sample. So I'm going to put y bar 1 and y bar 2 to indicate this is from sample 1 versus sample 2. Maybe I calculate, draw another sample, random sample 3, also of size 12, and I calculate the mean of that sample. And I do this again. The sample, and I do it again and again and again. So take many, many samples. Many samples, and each time we calculate the sample mean. And I'm going to keep track of all the different sample means that I've calculated. There's lots of sample means. I keep track of them all. And at the end, I create a histogram of all the different sample means. Or create a probability distribution. But let's, so we keep track. All the y bars. Okay, and then let's make a we're going to make a histogram of the y bars. Okay, what kind of properties will the distribution of y bar have? Or what will this histogram look like? Okay. Well, this is the discussion of the sampling distribution. So shall we try this out? Okay. So I'm gonna bring back screen here. Here. Okay, so I'm going to simulate this in R. So we first have to talk about what our parent population looks like. Okay, so I'm going to just create make the parent population to be normal. Okay, so population will have a normal distribution. So I'm just writing this in text with the pound sign to indicate this is the comment. And so I'm just going to create an object called pop. And let's round off. That might be too many. 100,000 random things with mean 100 and standard deviation equal to 16. Okay, so this might be something like, this might look like a normal distribution of IQ scores. And so I can just say, create a histogram of the population. This is what it looks like. Let's add some more breaks. 20. Alright, so we'll add 50 breaks, and let's do this. 4160. Okay. So this is what our population looks like. Okay. This is so our population has 100,000 entries in it, and their entries are, if I just look at the first 40 entries in population, we see this is what the different values we might see in the population. So first one is, this is IQ scores. First one is someone with an IQ of 111, someone else has an IQ of 99, then an IQ of 85, and we have a wide range of different IQ scores here. Okay. And I got 100,000, and so I've got quite the range of IQs. All right. What I'm going to do is I'm going to take samples of size. Oh, yes?
So when you say breaks of 50 and 20, what is that?
I'm telling R to change the bin width. And breaks just means it's kind of a measure of how many bins you want. It's not an exact thing. So if you say make 20 bins, or breaks is equal to 20, it'll try to make about something in the ballpark of 20 bins. It may not be exactly 20. And if I say make breaks equals 50, that increases the number of bins. So it just gives us kind of a little bit more of a granular view of our histogram.
And then the histogram that we're looking at, it's the last one, right? Where it says breaks 50.
Yeah, and I'm just creating, because the if I look at the minimum value of the population and the maximum value of the population, we see we get these extreme values here, okay? But these are so rare that they're kind of throwing off the scales of my histogram. And so I'm just kind of, just for the illustration of the histogram, I'm not discarding the data, they exist. But just so the histogram looks quote unquote better, I'm cutting those off, okay? Because technically there is somebody down here at 27, okay? But there's probably only one entry of that low. So I'm just saying, okay, let's just set the bounds of our histogram out here. Okay, so we get a better view of what's in there. Okay, is that all right? We can make the view larger if we wish. Okay, so, and I can ask, what is the mean of my population? And we see the mean, if I took the mean of all 100,000 people, the exact value of the mean for the population is 100.0315. This is the true exact mean because this is the mean of all 100,000 people in this population. Okay. So it could be, the state of, how many people are in the state of Wyoming? I think less than 100,000 actually. But something like this. You know, we've got a population, this is everybody, this is the true mean. And we can get the standard deviation of the population, this is the true standard deviation. So that's what we have. Okay, so I'm going to take a sample. So I can say sample, and what this does is it takes a random sample. I've got the IQ scores of all 100,000 people. And I'm going to say take a sample from population and take 10 random people from the population. Okay. And so these are 10 people that it selected. Okay. And every time I ask R to take a sample, it's going to take another 10 random people. Okay. And so every time I ask for a sample, it gives me back a different selection of 10 people. So it goes in and chooses 10 people at random. So what I want to do is I want to repeat this many, many, many times, okay? So I can ask, you know, let's create a sample X, and I'm just putting parentheses around this so I can actually see what happened, okay? And so here I said, give me X, and X are these 10 people, and I can ask, you know, what is the mean of X? And it says, okay, these 10 people I selected, the mean of their IQ scores is 109.5. If I ask for another new sample of 10, and I ask what's the mean of these 10 people, it tells me that the average IQ of these 10 people is 97.9. And I can do this again and again. Each time I get a new sample of 10 people, and it says this time, when you took a random sample of 10 people, the mean IQ of these 10 people they selected is 103.19. Okay. Can we see what's happening here? So the command sample is asking R, take a random sample from the population of 100,000 people, take 10 random people from that population, and then the next line says calculate the mean of those 10 people. All right, are there any questions with this? Yes?
So I understand everything except for each, the break thing. How do you get that number? How do you choose 50?
That was just an arbitrary thing.
It's not a specific.
And it was just to change the look of my histogram. Okay, if I go with the default, if I just say give me a histogram of the population, it looks like this. Okay? So all I'm doing is with my command, I'm just saying, okay, let's change the
Like breaking it up more?
let's just change the limits on the x-axis, and then I want a little bit more, a few more bins there. So I'm just saying, okay, let's do breaks equals 50. And that's just an arbitrary number, okay? I could do like breaks equals 500, and it tries to add a whole bunch of things, and you can see, you know, now we see a little bit of jagged edges here. Yeah?
And so, like, no matter what your histogram looks like, so it doesn't matter if you have 50 or 500, the mean, if we keep doing that command, the sample of population 10, it'll be the same, right? It doesn't matter what your histogram looks like? Because, like, if I were to do this, just for future reference, if I'm using this program, and I'm making, like, a histogram, and I do breaks of 500, but if I'm putting in the command, like, sample population 10, it's going to be the same, right? It doesn't matter what my histogram looks like.
Right. No, the histogram is an entirely separate thing. This is just for illustration, okay? The histogram command does not modify the data itself. It does not modify the data itself. Neither does sample, okay? The entries in population are that, okay? And actually, if we look at this histogram, we see tiny little bars. What's going on here? Okay, can you see that there's tiny little bars? Maybe only those of you in the front row. But there's tiny little bars. And what's going on is that, I don't know if there's any way I can make this any bigger. Is that when I generated my data for the IQs, it's only giving me whole numbers, okay? And so it's creating a bar at 100 and creating a separate bar at 101. And because I've asked for so many bins, such a tiny bin width, that it's not going to create a bar for 100.5 or something like that. Okay, so anyway, it doesn't matter. So the breaks, this only just changes the look of the histogram, not the data itself. This is the exact same underlying data, and it just changes the looks of the histogram here. All right, so anyway, I have the sample. I'm doing the sample thing, and I want to do this a whole bunch of times. Each time I want to calculate the mean of x. Okay, so I'm going to create something called samples. All right, and in the beginning, I'm just going to put in the value 0. But this is just going to be a placeholder. And what I'm going to do is I'm going to tell R to basically take a random sample of 10, calculate the mean of that. Actually, I don't want to do samples. Let me get rid of samples. I want to keep track of the sample means. Okay, so I'm going to create a spot called sample means. Right now, the value in the sample means is 0, but we're going to create a loop here. Okay, so I'm just going to say. I'm going to do this 10,000 times. And what I want R to do is take a sample, from population, take 10, size 10, and then I want you to calculate the mean of x. And that's going to be stored in sample means in location I within sample means. Okay, so basically all I'm doing is I'm doing the exact same code where I'm taking the sample from population of size 10 and I'm calculating the mean. The only difference here is that I'm putting it inside this for statement. And that just means do this a whole bunch of times, okay? Start with I equal to 1, and then once you run it through, it's going to increment I to 2, and do it again. I equals 3, keep going until I equals 10,000. So it's going to do this 10,000 times. And every time, I want you to take a new sample, put the sample into x, calculate the mean of x, and take the mean, that mean that you calculate, and put it into sample.means bracket I. So the first time it runs, it's going to be sample.means 1. The second time it runs, it's going to be sample means 2. And basically, you can think of sample means as like a folder or a file bin with location 1, location 2, location 3, all the way up to location 10,000. And every time it runs through, it's going to go to the next location and it's going to store that mean from the sample. Does that make sense? Okay, so I'm just going to run this. So it's doing this 10,000 times, and now it's done. Okay, and we can see that I has 10,000 in there. Okay, and we can look at, what does the first 10 entries in I look like? I'm getting, I'm sorry, not I. Sample means, sample.means. Okay, so the first 10 entries in sample.means, the first one is 93.9, and the next one is 96.5, and then I get 109.1, and so I get a whole bunch of different values in there. Okay. Is there a question? Yeah.
You you type in RM samples, what is the RM sample?
Oh, remove.
Oh, remove, okay.
I'm just deleting that thing. Okay, so because I decided I didn't want to call it samples, I want to call it sample means. That's all. Yes?
Where does the answer where does it show up?
What do you mean the answer?
The mean, sample mean? Because you were like, and then it's done, and is it up under values?
Yeah, so it's stored in my my workspace. Okay, so sample means it used to have the entry 0, but I've updated it, and so now there's 1 through 10,000 entries. Okay. And so now I can create a histogram of sample means. So what do you think this histogram is going to look like?
Normal distribution.
Normal distribution, okay. What do you think the center of this normal distribution is going to be?
The mean. 100.
Okay, and what about the standard deviation?
0.
What do you think the standard deviation of our sampling distribution is going to be? Okay, so remember our population, the mean of our population is 100.03. The standard deviation of our population is 16. Okay, so let's look at a histogram of sample.means. Looks like the same thing, except if we look at the scale, so let's make a histogram of the population. Where did this thing go? So I'm going to just use the same scale, and I'm going to still ask for 50 breaks, and I'm going to do sample.means. Okay, let's take a look. Using the same scaling, this is what the histogram of sample means looks like. So what happened here? The spread got smaller, right? Okay, so this is the histograms of sample means. If we leave it on the same scale as the population, this is what our histogram looks like. Okay, so it still has a normal shape. That's expected. Okay, our population is normal. And what we're doing is we're taking 10 random people from the population. When we take 10 random people from the population, it becomes very unlikely for the average of all 10 people to have an average IQ down here of 40. And it also becomes very unlikely to have an average IQ way up here. Because in order to have an average IQ way up here, that means all 10 people needs to have an average up here, okay? So you might get a few geniuses or someone who have very high IQs, but every time you take a random person of 10, it's also very possible that you get someone with a lower IQ. And that's going to bring your average down, okay? So when you're taking random samples of 10, we see that we're much more likely to get something very close to 100. Okay, and we can observe, check the statistics of sample means ourselves. We can ask, what is the mean of sample.means? And we see that the mean is very close to the mean of the population. Mean of the population is 100.03. Mean of the sample means is 100.02. Pretty much the same. But we can ask, what's the standard deviation of sample means? And we see that the standard deviation is much, much smaller. Whereas the population had a standard deviation of 16, standard deviation of our sample means is around 5. Is that good? Yes, question?
So do you consider this just condensing your data, basically?
Condensing our data? Yeah.
Not condensing, like fine-tuning, or?
No. So this is our sampling distribution. I hesitate to use any of these other words to describe what's going on, because we're not changing the data itself. We're not condensing it. We're just taking samples of size 10, calculating the mean of those samples, and looking at the distribution of the sample means. That's what a sampling distribution is. Okay, so does this concept of sampling distribution Make sense? Okay. What would happen if instead of taking samples of size 10, I took samples of size 3? You have a guess?
The spread might be wider than it is with 10 because you could have.
Yeah, okay, so let's
and less to like move it up.
all right, let's try this. Okay, so I'm going to basically run this same code. Except I'm going to get rid of these pluses because it's going to forget on me. I'm going to take samples of size 3. Okay, so let me just clear out sample means. I'm going to put in 0 there. And I'm going to just run this code. So it's the exact same code. I'm doing this 10,000 times, but I'm only taking samples of size 3. Alright. Let's take a look at this histogram here. So we're going to make a histogram of sample means. Same command as we have here. So the x-axis has the same scaling. This time we're looking at sample means when we took samples of size 3. And indeed, we see normal distribution shape, but the spread is wider. Okay? Not as large as our population itself, but that's expected because we're taking samples of size 3. We can ask what is the mean of the sample means. Something very close to 100 as well. And we can ask what's the standard deviation. So we get something in between. When we took samples of size 10, samples of size 10, the standard deviation was 9. Population has a standard deviation of 16. And when we took samples of size 3, we're getting standard deviation of 9.16. Alright. Okay, and what if I took samples of size 30 rather than size 10? What would happen? Yeah. Our sampling distribution would get very small. Or the spread of our sampling distribution will get very small. So if I leave the axis scaling the same from 40 to 160, we see that it's very tiny. And we can ask for the mean. Mean of the standard deviation, pretty much the same, and the standard deviation is even smaller at 2.92. Okay. All right. Is this kind of neat that we can do this in R and create these sampling distributions and commands? Okay, what would happen? So here our population was normally distributed. Okay, our population was normal. What would happen if our population was not normally distributed? Okay, so let's try this out. I'm going to create a new population. I'm going to call it pop2. And I'm going to ask it to create 50,000 with mean equal to, so let's create, let's make a bimodal distribution here. Okay, so we'll do a mean 60, standard deviation equal to 3, and R norm 5 times another 50,000 with mean equal to 70 and a standard deviation equal to 3. Alright, so let's take a look at what our population 2 looks like. Now let's add some breaks here. Okay, and let's just establish our x limits to 50 to 80. Okay, so I've got a bimodal distribution here. Yes?
Is it necessary to do those 3 steps? First entering the population, then the breaks, then the limits, or can you just do?
We can jump straight to the last one, okay? But I wanted to. I don't know what the histogram looks like, So first I just ask for, give me a histogram, and then I can take a look at it. And then based on that, I'm like, okay, well, I want to see more breaks, so I added more breaks. And then I said, okay, well, let's just cut off the limits too. Okay, so I've got a bimodal distribution here. So if I take, let's say I take samples of, forgive me, I'm going to regenerate this. I'm going to make my thing even more bimodal by changing the string. Okay, so now I've got something really bimodal. I wanted to change that up. Okay, is that all right? So I've got my population. This is my population, and it's bimodal. So what would happen if I took random samples here? Just round everything. Okay, so let's just take a sample from population 2, samples of size 10. Let's see what values we get, okay? So the two means that exist in our histogram, I've got one peak centered at 60 and one peak centered at 70, okay? And we can kind of see that when we look at the observed values. I get values that are pretty close to 60 quite often and pretty close to 70, and only once do I get a value that's kind of in between. Okay, so 59.9, very close to 60, also very close to 60, very close to 70, very close to 60, close to 60, close to 70. Okay, and if I ask for another sample of size 10, we should see something very similar as well. Okay. All right, what if I only take samples of size 2? What kind of things will I see? So sometimes I'll get one value that's close to 70, one value that's close to 60. Other times I'll get two values closer to 60. Sometimes I'll get two values closer to 70. Okay. So what do you think would happen if we run our code, and we're going to sample from population 2, and I'm only going to take samples of size 2. So from my population, which is very bimodal, I'm only going to select two people at a time. And we want to create, a histogram based on this. So I do this. Population is, this thing runs very slowly, and it's because I have 1 million in my population. So I'm just going to, just to speed things up, I'm going to just make my population only 100,000 rather than 1 million. But the population still looks the same. Okay, so let me just run this code again. Yes?
That top part in RStudio,
Uh-huh.
where you have the code,
Uh-huh.
how did that get up there?
How did that get up there? Okay, so generally it looks like this, and you can just do File, New File, RScript, or there's a bunch of other things you can do, okay? But start off with RScript and it creates kind of this blank area, and this is where you can, if you're gonna work on something, you can type it up there, and then you can just modify it, and then click the Run command.
And then it goes into.
And it goes into the console and it runs it for you. Okay. Okay, so this is what we got. What do you think our histogram is going to look like if I look at the histogram of sample
You need
means?
a bigger histogram.
So let's do the same thing. Sample means using the same scale from 50 to 80. I'm taking, this is the mean of size sample 2. So what do we see here? Our distribution now has 3 peaks. Okay, so what's going on? Why am I seeing 3 peaks? I'm taking samples of size 2.
Because they're closer to like either 50, 70, or 60.
Okay, so I've got, so the original bimodal distribution has a peak centered at 60 and a peak centered at 70, right? So when I'm taking samples of 2, both of them might come out close to 60, both of them might come out close to 70, or I might get one close to 60 and one close to 70, all right? And